Hi, I'm David Castellrufas. I work in the Universitat Autònoma de Barcelona, and I'm going to present our work in collaboration with the company Maxa on the speed limits of single beam laser marking. Here you can see the outline of my talk. After introducing the problem, I will cover all the aspects that can introduce a constraint into the line speed. First, the marking surface, the details of the laser source, the deflection methods, and the computing systems. Then I will discuss about the implications of the analysis. We will follow by analyzing multi-beam systems before concluding. Laser marking has a number of benefits over other marking methods. It is easy to integrate, it uses no consumables, and has a very low maintenance. This is why it's commonly integrated in production lines of many manufacturing industries. Such marking systems typically include a motion sensor that coordinates the conveyor movement with the marking process in real time. Industry demands laser marking systems at continuously higher speeds. One of the reasons is the requirement of tracking all manufacturer goods in the context of Industry 4.0. But single-beam laser systems face a de facto limit around 8 meters per second. In this work, we analyze what are the causes of this limit and if it is possible to surpass it. Materials react differently depending on the parameters of the laser beam. Its irradiance, its wavelength, the beam spot distribution, the interaction time, they all can produce different effects on surfaces. However, they are commonly based on thermal phenomena, so heat. Heat is produced by fluence, which is the integration of irradiance over time. Depending on the material, different physiochemical processes can be triggered. For instance, in organic material, carbonization can occur. On other surfaces, high-power beams can trigger ablation. Melting is typically used in plastics and metals. Depending on the material, the processes that cause the visual effect start at some irradiance and fluence thresholds. Since fluence depends on time and irradiance cannot be increased at will, the fluence threshold already imposes a constraint on the scribing speed. But actually there is some margin to increase the irradiance, either reducing the beam spot size or increasing the laser power. While continuous wave lasers are sometimes modulated to reduce power, pulsed lasers use a duty cycle to do the contrary, pump up all the energy to produce very short energetic pulses. In pulsed lasers, the pulses are so short that even when moving at high speeds, the beam spot during the pulse has an imperceptible displacement. However, the inactive part of the pulse can be large, and the pitch between the dots that it creates can be actually a limiting factor to increase the speed. In slower modulated lasers, the movement during the active part of the pulse can be important. In this case, the limiting factor to increase the scribing speed will be the maximum allowed aspect ratio that our application can tolerate. But static beam is not enough to mark a surface. We need to deflect it to cover 2 dimensions. There are many single beam deflection systems. Polygonal mirrors and AOD and EOD are some of the fastest, but in practice galvanometers are more versatile and cost effective. Looking at the state of the art, the fastest deflection systems have a scribing speed below 300 meters per second with polygonal mirrors and below 20 meters per second with galvanometers. As we will see later, this is one of the main constraints to surpass the de facto limit of 8 meters per second. The concept of digital printing on laser marking equipment involves the need of updating every printed image by an external computer during operation. We create a simple analytical model to estimate bandwidth to transfer input images, the maximum allowed latency to correct positioning errors, and the required computing throughput. In the table, we describe 2 scenarios running at a line speed of 20 meters per second to check if the requirements are attainable with the currently available computing platforms. The results show that there is an important safe margin before computing platforms will be the bottleneck. Reviewing the different factors, we can note that the surface can impose a serious constraint if the material has a specific combination of irradiance and fluence to produce the desired visual effect. The laser source can also be a limiting factor, especially when using the pulsed lasers with low pulse repetition rate. On the other hand, the option to increase the laser power to reduce the time to reach the required fluence can be too expensive in many occasions. Deflecting systems are the currently most limiting factor as they are not expected to improve drastically from the current maximum scribing speed values. The scribing speed is the speed of the beam in its raw scanning path, but this path has to cover two dimensions. Line speed is the speed of the marking process in one of the axes, aligned with the conveyor movement. The wider the width of the marking area, the longer it will take to complete a row, and the slower the line speed. The only viable option we can foresee to overcome these limitations is the use of multiple beam systems. We believe that the most promising technologies are laser diode arrays and digital micromirrors. By using multiple beams, we can remove the raw scan constraint of single beam systems and replicate as many beams as required to make the line speed as close to the scribing speed as possible. In diode arrays, we can place the diodes close to the surface without requiring moving parts. Power density will be the challenge to solve for such systems. In micromirror-based systems, the challenge will be to manufacture devices that are not damaged by the irradiation of the mirror arrays, since the fill factor cannot be always 100%. Thanks for your attention.